Welcome back. Today we're going to be talking about some properties of binomial coefficients. Let's start by looking at Pascal's triangle, since these give us binomial coefficients, right? If you'll recall, for example, this 1 here is 0, choose 0. This one is 1, choose 0. We have 1, choose 1. 2, choose 0. 2, choose 1. And 2, choose 2. And this pattern repeats all the way down the triangle, right? So by looking at the triangle, we can gain some insights for possible properties of these binomial coefficients. Okay, I'm going to erase these now, and let's look at some properties. So I think one that's pretty clear by looking at it is it has a sort of central symmetry, right? If I draw this kind of dividing line here, the left side looks like the right side, right? So what can we conjecture from this? So maybe I'll write this as number 1 is symmetry, right? So what does this possibly tell us? Well, maybe it would be helpful to look at with this row, for example, because this row is 0, 1, 2, 3, 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, and 4, choose 4. So let's say from this row, we can kind of see we have that 4, choose 0 equals 4, choose 4. We have that 4, choose 1 equals 4, choose 3. And 4, choose 2 is obviously equal to itself, right? So I think the general pattern here should be n choose k equals n choose n minus k, right? This is the generalization of this pattern that we've observed. Is this true? I guess we'll find out. What about another property? So I think the other property here that's perhaps kind of interesting, I'm going to erase these here, is the sum of the rows, right? Maybe I'll put down a little column here. So if I label this each row, let's say, so I'll put this as, we'll say this is row 0, this is row 1, this is row 2, row 3, row 4, row 5, right? On the other side, I put the sum of each row. Okay, the sum of this row is just 1. This row is 1 plus 1, which is 2. This row is 1 plus 2 plus 1, which is 4. The next row is 1 plus 3 plus 1, which is 8. Then, well, some more math will show you. This is 16, and this is 32. Interesting. These are the powers of 2, right? So it sort of tells us here that each row sum equals 2 to the row, basically, right? But what does this really mean, right? What is a more precise statement here? It's that when you sum up all the binomial coefficients from k equals 0 to n of n choose k, this is the row sum, right? We get 2 to the row, which is n. So these are our two conjectures, let's say. We have not proven these, but looking at Pascal's triangle gives us a hint that these should be true. Okay, let's go and prove them. Starting with n choose k equals n choose n minus k. And for each of these, I'm going to offer a few different proofs just to emphasize that there's also different ways to prove things with binomial coefficients. These numbers have so many great properties that they're sort of a dream to work with when it comes to proofs. You have lots of ways to prove things with them. Let's start with the formula, which I think is the most direct way of seeing this. Okay, what's the proof here? Well, n choose k equals n factorial over k factorial n minus k factorial. And, well, maybe you can guess what the next step is here, but this is literally just the same as n minus k factorial times n minus k factorial, right? Since this here, this is just k factorial, right? But then what is this? just by the definition, or rather by the formula that we have for these binomial coefficients, this is just n choose n minus k. Okay, so this is probably the most direct way of seeing this. But that's not the only way to see this. What about using the binomial theorem? Well, again, let's just write it out, right? We have that x plus y to the n equals the sum from k equals 0 to n of n choose k, x to the k, y to the n minus k, right? Okay. But keep in mind, as k goes from 0 to n, so does n minus k. So this is really the same as the sum from k equals 0 to n of n choose n minus k times x to the n minus k, y to the k. Okay. But now, x plus y to the n, this is just the same as y plus x to the n. Okay. But what is y plus x to the n? It's just the sum from k equals 0 to n of n choose k, y to the k, x to the n minus k. So all the coefficients match up here, right? This is true for any x and y. And so this tells us that n choose k must be equal to n choose n minus k. That's a bit more of an indirect way of seeing it. But I think the equation itself, mainly this, already gives you kind of the hint behind this sort of symmetry, right? Okay, great. Let's move on now. The counting proof. Now these are oftentimes fun because this lets us kind of leave the world of all the algebra for a little bit and really think about what the statement is saying. Okay, so what is n choose k? In terms of its kind of counting definition, it's the number of ways, I'm going to be a little imprecise here, to choose k things from n things. But this is really the same as the number of ways to not choose n minus k things from n things, right? Because choosing k things is essentially the same as just not choosing everything else, right? You can imagine if you are, let's say, choosing 3 students for a student committee from 5 people, that's the same as essentially choosing the 2 that won't be on the committee, okay? But then what's the number of ways to not choose n minus k things from n things? This is basically just the number of ways to choose n minus k things from n things, right? The number of ways not to choose 2 out of 5 is still the same as the number of ways to choose 2 out of 5. So this is just n choose n minus k. And this is kind of my favorite explanation for this property. All right, this literally is just because when you're choosing k things from n things, you're implicitly not choosing n minus k things. Right? So they're kind of the same thing. Okay. Let's move on to the row sum property. This one I think is a little more mysterious. I sure wouldn't immediately guess that it's true, but it has some really nice proofs. I would say the simplest one is due to the binomial theorem, which is, okay, what is 2 to the n? This is 1 plus 1 to the n. Okay, no big surprise, but now we can use the binomial theorem, right? This is just the sum from k equals 0 to n of n choose k, 1 to the k, 1 to the n minus k. What does this equal? We're just raising 1s to a bunch of power, so those are all just 1. This is just the sum of the n choose k's, right? That's it. That's simple. Okay. Not very instructive, I guess, but very quick. It gets the point across. The Pascal's triangle proof here, I think, is a little bit more interesting. I think this one I won't kind of write out in full rigorous detail, but I'll more so show an example. Let's just write out some entries of Pascal's triangle here. Okay, let's say I look at this row, right, this blue row, and I look at this row, right? And, okay, I ask the sum of this row, right? Say the sum here should be equal to twice the sum above it, right? If we can show this, then we would have proven the proposition. Why should this be true? Well, what is this sum, right? So this sum, it's equal to 1 plus 3 plus 3 plus 1. But where do these numbers really come from? Well, okay, this 1 here came from 1 plus 0, right? This is just summing the two things above it. Remember, in Pascal's triangle, everything else here is just like zeros everywhere else, right? So this 1 came from 1 plus 0. What about the 3? Well, the 3 came from 1 plus 2. The other 3 also came from 1 plus 2. And the 1 again came from 1 plus 0. But now, what we've essentially written out is we've just written out all the entries in the row twice, right? So, what do I mean by that? We have 2 times, well, we have a 0, we have a 1, we have a 2, and we have a 1, right? Since everything here appears in the sum twice, we can just take out the 2. Okay, and this is just 2 times the sum, right? And that's it. What it essentially tells us is that as long as the sum of the first row, or rather, I guess, row 0, as I labeled it before, as long as the sum of that row is 1, and each row below it will have a sum of double the row above it, then the sums will be the powers of 2. Okay. But there's one last proof here, which is definitely the most complicated, but it's also my favorite. And I think it's a really nice way to remember this property. Okay. So here's the question. What is the number of subsets, I'll say of any size, of an n-element set, but I'll just do 1, 2, up to n, right? What is this? Okay. Maybe I'll give this number a special name. I'll call it, let's say Cn. Okay. This is just what I'm calling it. So what is Cn, right? Well, okay, on the one hand, Cn is the number of subsets of size 0 plus the number of subsets of size 1, yada yada, all the way up to the number of subsets of size n. But what is the number of subsets of size 0? This is just n choose 0. The number of subsets of size 1, n choose 1, so and so on, up to n choose n, right? This is the sum from k equals 0 to n of n choose k. This is one side of our equation. But, okay, what's another way of looking at this? Well, there's another way we can kind of think about finding any subset of 1, 2, up to n. And that's by choosing or not choosing each element one at a time. What do I mean by that? So let's say we have our set 1, 2, up to n. We can kind of go down the list and make a binary choice for each one. So I'm going to color this in green and red, I think. So essentially, we can say, okay, I want 1 in my set, or I don't want 1 in my set. okay? And I can go to 2, and I can say I either want 2 in my set, or I don't want 2 in my set. And I go down the list up to n, where I either decide if I want n in my set, or I don't want n in my set. Okay. So what we're essentially doing here is making n binary choices, right? By binary here, I just mean 2 options, right? So essentially, choosing a subset of this set is really the same as making n binary choices, right? You're essentially saying yes or no to each element. So then Cn is the number of ways to make n binary choices. But what is this? Well, we have 2 choices, or 2 options for the first choice. We have 2 options for the second choice. And we multiply these together because they're independent choices. Right? One choice does not influence the other in any way. So we have 2 choices, whether or not to include 1. We have 2 choices, whether or not to include 2. We just multiply that down the line up to n, right? And there's n of these 2's. And so this is just 2 to the n. And this proves it, right? Because we've shown that Cn is the sum of the binomial coefficients, and also that it's 2 to the n. Okay, there we go. Those are some nice properties of binomial coefficients and many different ways to prove them. You'll notice, in general, when working with binomial coefficients, that there's always a few different ways to prove things. There's counting arguments like this one. The binomial theorem can often be a source of very short proofs as well. Or using the formula involving factorials. Really being comfortable with all these techniques is very important when you're working with binomial coefficients. Okay, thank you for watching.